Hello and welcome again. My name is Łukasz Łukowski. I'm working at STORDIS, and together with me today is my colleague Don. We will try to bring you more the unique solutions from the company called Credo. So the topic of today is active electrical cables enabling the future of the high Radix interconnects in the data center. And to be more precisely, we will help you with the data center spaghetti on the highest 400G speed as we speak. So Don, once again, thank you and appreciate to joining that first webinar with us. We are also delighted to start the cooperation. I will say that from my end, that was something, it means your portfolio, it is something that really is missing today in our open networking focus. So I am even more delighted to have you here. Could you just introduce and say a few words about yourself,
Thank you so much for having us. We're excited to partner with you as well. My name is Don Barnetson. I'm responsible for the HiWire cable products at Credo. Credo is a semiconductor and cable manufacturer with offices in San Jose, Shanghai, and many other places. But today we're here to talk about our active electrical cables in some detail. So we'll do a quick introduction to the company. We'll talk about these distributed disaggregated chassis, which have gotten a lot of interest recently. And then most interesting for us, we'll talk about the fabric that stitches them together. What are the options? What are the trade-offs and challenges? Spend just a moment on the Credo products that are relevant, and then get into hopefully some interesting questions.
Absolutely. So maybe also from the technical perspective, please feel free to ask any questions. In the end, we will try to go over a short Q&A. Also on your right side, you will find the chat section. So please feel free to use it. But also in the end, there is that handouts section where you are able to download some interesting datasheet materials. Just inviting you to go there. The stage is yours.
Thank you. A message from our legal department, as they say, make sure you read every word. On to Credo. So Credo, as I mentioned, enables every connection in the data center. We have 3 major lines of business. We build line card PHYs, so these IPs, chiplets, a variety of different solutions to allow servers and switches to connect to each other. We build optical DSPs that go inside of the transceivers and AOCs that you're familiar with throughout the speed range. And then the focus on the right today are the HiWire AECs. So we build them for 2 major segments. The distributed disaggregated chassis we're going to talk about today, the DDCs. And then I think at a future discussion, we're going to talk about the NIC to TOR AECs, which is also a very exciting segment. If we look at a traditional hyperscale data center, typically it's a fat tree architecture, as I've shown here. So you have servers at the bottom. That first layer of switching, the top of rack switch is called T0 in this nomenclature, borrowed from our friends at Microsoft. The row spine, also known as the leaf, is called T1 in yellow there. And then it comes together at the data center spine in purple, called T2 here. So in this traditional architecture, you use a pizza box structure at T0 and T1 because you're really making relatively low radix connections to move data primarily north-south. But at T2 and T3, you're really connecting across the fuller data center to allow that east-west traffic, and therefore you need quite high radix connections. In a traditional structure, you would use a chassis for these T2 connections. And so a chassis, I think probably many of you are familiar with, is basically a big metal box that has a number of line cards and fabric cards that slide in and out of it. And then those cards are connected with each other on the back plane. And so there's a very expensive large circuit board on the backside with many, many connectors that allows all of those line cards to connect to each other. And logically, you have something that looks like what you see on the right. So each one of those line cards might have 16 or 32 external ports, which you would traditionally plug with optics. And then on the back of that line card, you have a large number of local connections building out this local cloth structure to allow the line cards to talk to each other. Importantly is you have a fixed chassis config. So you really do need to forklift this big metal box into your data center. And once you do so, it's designed to take a specific number of these line cards, and that is it. You have proprietary hardware. Once you put the box in your data center, you have to buy the line cards from that same company. They tend to be fairly expensive. And then maybe most importantly, you have proprietary software. So traditionally, these chassis run captive software from that maker. You're probably familiar with the names. And often that software has quite a legacy to it and may not run in the most modern way that we've become accustomed to. So the large hyperscalers have started to move away from this. Some of them have been doing it for a long time. Some of them are new to this. So rather than buying a large chassis and putting it at T2, they take a large number of pizza boxes and they connect them together on the front panel with standards-based interconnect. And so that allows them to logically build something that's similar. You can see the schematic on the far right is functionally similar to what the chassis had, but you've built it out of commodity hardware and commodity interconnect. And that allows you to do a couple of important things. First of all, you can build whatever you want. You don't have to put this big metal box in place, and then you're stuck buying whatever hardware that vendor has. You can use interchangeable white box hardware from a variety of vendors. Probably most important, you have choice in software. So there are a variety of open source software solutions. There are a variety of third-party software solutions, many choices depending on exactly what your needs and budget are. And then most interesting for us is you use standards-based front panel interconnect. And so that actually gives you a lot of choice in front panel interconnect depending on what problem you are trying to solve. So DDCs started with AT&T. All the way on the left side, AT&T made a submission to the Open Compute project about 4 years ago, describing how they were going to take their core routers from a traditional chassis-based structure to a DDC. And that first router they described is the one that we built in the middle here. It is the Jericho 2 Ramon cluster, in this case, a medium cluster. So this one has 24 what they will call network cloud processors, what you can think of really as line cards. And in this picture, they're on the left and the right. There's 12 of them in each of those racks. Each one of those line cards has 4 terabits per second of external facing optics bandwidth. And then they come together in these network cloud fabrics, these NCFs, which are in the middle rack. And each one of those has about 19 terabits of bandwidth. So the total bandwidth of this 3-rack solution was approximately 96 terabits. And then the power, if you remove the optics, the power of this system was about 100 watts per 400 gig port. So what's interesting about DDCs is just how fast they are moving. So AT&T described this 4 years ago. The industry built and showed it. I believe we had it, this one in the middle, ready for OCP 2020, which unfortunately did not occur. But in just 1 year, at OCP in 2021, we showed the Jericho 2C Plus version on the right-hand side. So the Jericho 2C Plus version, the NCPs move from 4 terabits to 14.4 terabits each. And then we added some additional NCFs. And so in the same amount of racking space, we actually roughly quadrupled the available bandwidth. So we have about 350 terabits of bandwidth in this space. And then maybe most interestingly, the power efficiency was doubled. And so rather than 100 watts per port, we're at 50 watts per port. You can see the density of front panel interconnect on that is starting to get quite high. There's almost 1,000 cables on that front panel. And we've cabled it in 2 different ways, perhaps that we can talk about later. On the left-hand side, we cabled laterally, which is more of a high-performance computing style cabling. And then on the right-hand side, a more traditional tray style, where all of the cables egress up vertically, loop over the tray, and then come back down. So this DDC Fabric Interconnect, you have some choices here, which is one of the things our customers find interesting. And so kind of a classic way to do this would be active optical cables, or AOCs. So an AOC is an optical cable, typically a multi-mode optical cable with DSPs on both ends. It's a fairly expensive item, and it's a fairly high power item. So I've normalized it roughly to the active electrical cables, which are the devices we make. But an AOC costs about twice as much and consumes about twice as much power. However, when you're routing at very high densities, it's a very thin cable because it's a fiber optic cable. So it's about 3 millimeters in diameter. It's about 25% of the volume of AOCs, or sorry, of AECs, which are quite attractive. So AECs, which are the products that we make, are copper cables, which have clock and data recovery retimers, so CDRs on both ends. These cost, in this normalized case, about 1x, so they're kind of our baseline cost. The power is 4.5 watts per N for a 400 gig cable, and they're about as thick as a Cat6 cable, about 6.8 millimeters in diameter for a 2.5 meter cable that we're using for this structure. And so what's interesting for our customers is when you look at the cost of ownership of this. So if you compare AECs to AOCs, as I mentioned, the acquisition cost is about 2 to 1. And so if you're building out that medium cluster that I showed on the left, it's about, the difference between $50,000 and $100,000 for the initial acquisition cost, as you can see in the year one budget. The power difference is also 2 to 1, and that starts to make a difference over the lifetime of the product. But what's most interesting, I think, for the customers is the reliability difference. AECs are copper cables. And copper cables don't have built-in wear-out mechanisms the way that optical cables do, and therefore we're able to deliver a reliability close to 100 million hours mean time between failure, which gives you an annual failure rate that's extremely low. You would not expect a cable failure in any of those chassis I showed in a 8 or 10-year lifetime. AOCs traditionally have wear-out mechanisms, in particular at the price points that the vendors are trying to build them at, and therefore they have an MTBF closer to 1 million hours, which gives you an annual failure rate closer to 1%. And so if you look at the cost of ownership over an 8-year cycle, you can see that AOCs have a cost of ownership of approximately $250,000 US. AECs are approximately 53% less. They cost less to buy, they cost less to power, and they cost less to maintain. And so they win pretty clearly in cases where they can be implemented. But you might be asking, what about passive cables? What about passive copper? Those are really inexpensive and really reliable. And you'd absolutely be right. So direct attached copper cables are passive copper cables, and because they don't have much in them, they are inexpensive. They cost about half as much as AECs, about 4 times less than AOCs, and they don't consume much power at all. So a traditional DAC just has a little bit of identification electronics in each end, consumes less than 1 watts per end. The challenge is at 400 gig, DACs have really gotten pretty thick here. And so at 400 gig, you're looking at about a 12 millimeter diameter DAC, which is about as thick as the garden hose that I have in my house outdoors. And so when you start to route those at high density, it becomes kind of problematic. Let me show you a picture here. So if you build this, this same rack structure with DACs, you end up with something that you see in the middle. In this example, we have about 150 pounds of cables, maybe 60 or 70 kilograms for those of you in Europe, hanging off the front of this rack, sticking about ½ meter off the front of the rack. This has all sorts of problems. It affects aisleway access. It is nearly impossible to maintain and actually change one of those switches. And it actually makes the entire rack structure kind of tippy. And so one of the tests that this rack has to pass is you have to be able to tip it 10 degrees and not have it topple over and kill somebody. And the cantilevering 60 or 70 kilograms worth of cables off the front end makes that quite difficult. By comparison, if you look at the AEC rack on the right-hand side, plenty of space, easy to maintain, something that is much, much more manufacturable. As we start to get to 800 gig, things get even more interesting. So I would say most of the development efforts in the industry are around 800 gig today, and it'll start to go mainstream next year. So if we look at a top view of a 1U switch, which is what I have tried to cartoon here, you see that there's a switch SoC in the middle that might be made by Broadcom or Marvell or any number of other companies. And then there's typically 32 ports across the front of that in 2 rows, 16 top and 16 bottom. And so if you want to support passive copper cables, DACs, you have to do something, you have to make a CR compliant port. And that starts to add cost to making an 800 gig switch. It makes the switch about 20% more expensive. And so the question is why? So what's happening is you have a very fixed loss budget. So you're only allowed to burn up about 7 dB of your loss budget between that SoC and the front port. And at 800 gig, what that means is the center 8 ports on each row, the center 16 ports, you can direct route on the PC board material, but you have to use a really expensive Megtron 8 class PC board dielectric to do so. The edge ports, the 8 on each side, you can't direct route because the trace lengths would be too long, and so you have to use flyover cables or retimers on those edge ports. Whereas if you just want to support active pluggables, you can use a much less expensive Megtron 7 dielectric everywhere, and you can just direct route all of the ports. So you get rid of the flyover cables or retimers, you get to use a Megtron 7 dielectric, you save something in the order of $1,000 on your switch cost. So it starts to become a really big deal, and what we're seeing today is already multiple switch makers have basically dropped CR compliance from their 800 gig switches. So what's the message here? DACs are dead. DACs are going away at the 800 gig generation because they really no longer solve end user problems. If you're routing them at these densities, they're not interesting. And they're driving cost and risk and complexity into the switches. And so people were making the right decision, which is to stop supporting them. And we'll see that over the coming years. So let me briefly talk about the active electrical cable families and how they fit into this. So we have 4 families of HiWire AECs today. On the left, we have our span products. These are AOC replacements. They are designed to span between racks. You can sort of see where these names might have come from. They're available in 200 and 400 gig versions up to 7 meters in length today. In the next column, we have our shift products. Our shift products have breakout and gearboxing functions built into them. So we're able to take 56 gig lanes and turn them into 28 gig lanes, or take a 400 gig side and break it into 4 100 gig sides. And so these are available in 200 and 400 gig sides on the stem on the fast side, and then we break out into 200 and 100 gig sides on the other end. The products that are most relevant for DDCs are in the third column. There are CLOS products or our CLO products, if you're more technically correct. These are specifically designed for DDCs. These are very, very thin cables, up to 2.5 meters in length, that are designed to support these very, very high density interconnects up to 1,000 cables per rack. And then all the way on the right-hand side, we have our switch cables. These are the ones I think we're going to talk about in our next webinar in about a month. These ones we actually designed with Microsoft for their data centers and are upstreamed in the Sonic operating system, as well as several other operating systems coming up. They're designed specifically for NIC to TOR connectivity. All of these cables are very reliable. They're all solid state copper cables, and all of them are designed to a prefec BER better than 1E-8. They should not be producing any post-FEC errors. So a couple of conclusions here for our early morning webinar. So DDCs really do provide tangible benefits over chassis. Most importantly for customers, you have better software. You have open source software, or you have third-party software. You have choice, but you generally have better, more modern software. There's many partners that we can talk about there. You have much more flexibility. So you no longer have to put a big metal box in your data center and then put things inside of that. You can build exactly what you want to suit your needs, and you can expand it and reconfigure it as necessary. As some of my colleagues at DriveNet say, this is a much more sustainable solution because you don't have to throw out these pieces if they don't exactly fit you. You can reconfigure and reconfigure this solution as your needs change. You have lower cost, multiple hardware sources producing white box hardware that are all equivalent and that are all supported by the open source or third-party software. Means lower cost because you don't have lock-in. And then, as we just talked about, standards-based front panel interconnect that's available from multiple vendors. So obviously we have a strong preference for active electrical cables, but you can choose what you need in order to do what you want to build the system that works best for you. However, we think that DDCs are absolutely best when built with AECs. AECs are half the cost and half the power of optics. And they consume up to 75% less volume than DACs. And if you've ever worked with 400 gig DACs, you know that your hands get tore up by these incredibly rigid, thick things. You just don't have that problem with AECs. It's much more maintainable, much more operationally optimized solution. And I think that is the content we put together this morning, Lucas.
That could be the case. That could be the case, and really appreciate. We have a few questions, so let me start that and also take a look. Yes, exactly. So we are going to the questions. So one of the questions which I collect, you mentioned that AECs are more reliable than optics. Why is that? And can you go a little bit deeper?
Yeah, sure. So optics are doing a couple of important things. So optics have an electrical front end, which is what makes contact with the system they're plugging into, and then they're doing a conversion to an optical run. So they have lasers, they have TIAs, they have amplifiers in order to make that optics conversion, which allows you to go over these tremendous distances, which is what makes modern infrastructure work. The challenge is at the price points that optics are being pushed to today. They would very much like to be hermetically sealed, but they can't be at the price points that we're pushing into today. And so you have wear out mechanisms that are built into these optics in the laser, in the diodes, in the interconnect, which age over time. And so those wear out mechanisms create an MTBF that is relatively poor compared to more traditional solid state solutions. Active electrical cables are fundamentally copper cables. And so copper doesn't wear out in this structure. We don't have something that ages or yellows or is otherwise damaged by oxygen and water in the air. And so these cables are able to run much more reliably, similar to a passive copper cable over a 10 or more year lifespan.
Okay, so maybe the question from the Richard: how do active copper cables compare with the AECs? So it is pretty obvious with the DACs, yeah, but it is more like a
sure. So active copper cables are a technology that a variety of different groups are promoting, and so they're using an analog amplifier inside of the cable in order to amplify the signal. And so the idea of the analog amplifier is that it's a very low cost and low power way to achieve some of the same objectives that AECs do, because you're able to drive the gauge of the cable down and you're able to extend the reach of the cable. The challenge of ACCs is there is no standard to build to. And so ACCs are typically on the far end of the cable amplifying the signal, but there's not any IEEE or MSA standard for what that signal should look like. And so if you are a very large manufacturer and you have unlimited technical resources, you can build ACCs, and we've seen these, which are tuned to each individual port in every switch that you make. So you plug it into port 23, there's a specific recipe for port 23, and some engineer sits there and hand tunes it to make it work. Unfortunately, most of our customers don't have the resource or interest to do so. Even in our large hyperscale customers, there's just not the interest to spend that much time making it work. They have other problems. AECs electrically function with a standard chip-to-module interface. And so they are natively supported by all of the switches today because they look just like an optic electrically. And so the benefit of AECs is they're standards-based, they're reliable, and they work. And therefore, the adoption of AECs is much broader than ACCs in the marketplace.
You also mentioned about the hyperscalers, but when do you see, like, the adoption is getting beyond those mentioned tier 1 hyperscalers with the DDCs?
Yeah. So today we're seeing a lot of tier 2 hyperscalers, software as a service companies picking up DDCs for their spines and for their routing layers. We're also seeing it in the service provider space, in the MNO or MSO space. AT&T was obviously really the group that sponsored DDCs into the ecosystem for their mobile networks. We're seeing quite a bit of adoption of that. And as the software and hardware ecosystem expands, we see more and more folks interested in DDCs rather than being interested in traditional chassis for all the reasons that we talked about. But I think most importantly, better software. The software that you can get on a DDC is often just so much more modern and superior to what you see in a traditional chassis.
Absolutely. And then, in general, going to the open networking flexibility on the software, flexibility on the hardware, no vendor routine. We know that well. You showed the portfolio. We went over those breakouts very quickly, but for me, it is basically something which was really buying me into your offer. So you have a unique technology. If we are speaking about the breakout cables and the 400G, could you explain those uniqueness, especially with the gearbox?
Yeah, sure. So one of the nice things about active electrical cables is because we're recovering the signal back to a digital space on both ends of the cable, we can then manipulate that. And so rather than just retiming that signal, we can actually gearbox that signal. And so one of our better known cables is a 400 gig to 4x100 gig. So it has a 400 gig DD or OSFP connector on one end, and then it has 4 QSFP28 connectors on the far end. So we call it our DD to 4Q cable, and that cable's doing a lot more than just propagating the signal. So on the 400 gig side, it's retiming the signal, and then it breaks into 4 physical cables. But on the 100 gig side, we're terminating the KP4 FEC. We're doing a baud rate shift from 2 lanes of 56 to 4 lanes of 28 gig. And then we're regenerating a KR4 FEC to give you a plug and play cable. So if you have a 12 terabit Tor with a 400 gig port in it, and let's say you have some ConnectX-5 class NICs, you can just plug them into each other with a standards cable, and it works right out of the box.
Or if you wanted to use some kind of like a super spine 400G, but split it into 4 times 100G. So based on the Tomahawk 3, you can get 128 times 100G and go to your, I don't know, Trident 3. You can do that because normally the guys in the open networking with the bare metal, unfortunately, to keep the costs down, they are not gearbox, and there is the issue. Yeah, simply you cannot connect it. Yeah, and going over the fibers is extremely expensive. We'll be doing some comparison. We need to go over the PAM4 and so on. That always is a challenge.
Absolutely. AECs, in that comparison to using a DR4 and 4 DR1s should be, around half the cost and half the power, which is the broad value proposition of AECs. And then, as I mentioned, a whole lot more reliable.
And the last one we can see from Mark. What do you see for form factors? We have QSFP-DD and QSFP being adopted. So that is always a challenge, yeah? So speaking also, what I see from the switch perspective, QSFP-DD, yes, most of the time on the 400G, or yes, only time, which I see from the edge core, from the UFI and so on. And then QSFP28, but there is plenty of others, yes? So interesting.
Well, yeah, that's what I was going to say. I wish it was just those 2 form factors. So if you look at the base of the form factors, the basic question is how many lanes does it support? So a QSFP supports 4 lanes, a QSFP-DD or an OSFP supports 8 lanes. And then the industry is working towards an OSFP XD, which will support 32, or which will support 16 lanes, 16 in each direction, so 32 physical connections. And so what we've seen in the 100 gig space is QSFP is absolutely the right solution. Today, 4 lanes of 25 or migrating to 2 lanes of 50. In the 400 gig space, QSFP-DD is the most dominant form factor today. 8 lanes of 56. There's a few people who use OSFP, but I would say the 2 solutions are kind of functionally equivalent. The downside of OSFP is the connector is a little bit wider. And so if you have a standard 19-inch rack, it forces some of the management ports onto the back side, which is kind of inconvenient. And so you don't see quite as much adoption of OSFP in the 400 gig space. The benefit of OSFP, however, is it has a much higher thermal envelope. So as we look forward into 800 gig and into the 1.6 terabit cables and optics, I think we're going to see much more use of OSFP in part for that reason, because you can dissipate the very high heat that these optics solutions will have, in particular as we move towards some coherent optics in this space.
Yeah, I believe that you are right here. Always it is going together. Unfortunately, that's a challenge.
It always gets harder.
I don't see any other question, but I know that this is not everything what we would like to share. So we would like to already invite you on our May meeting. So that will be 19th of the May. I believe that at the same time, soon we will be also introducing that one, where we will show more details about the modern way of, let's say, virtual MLAG. Hopefully that is a little bit not too far, but we will explain that later on. So I'm also looking forward. Once again, thank you and appreciate for your time, Don. It was a pleasure to have you here. If someone would like to reach out to us, please always feel free. We will be doing some kind of like a follow-up. Those all materials will be provided to you, like always, same as the contact details to Don or to me. Once again, thank you. Always a pleasure to talk with you, and I'm really looking forward for our May meeting. That will be a great combination, not only about your dual Tor technology, but we will also go to some interesting software options.
Sounds great. I can't wait. Well, thank you so much, Łukasz.
Thank you, Dan. All the best.